Okay, thank you. Good evening, all. This is Dewey Caron. I'm coordinator with a committee of a couple individuals for the WASP mini conferences. Welcome you this evening. I'm apologize that we've had to make a change in what our program was for this month in May. The scheduled speaker, Garrett Slater, who is at USDA lab in Baton Rouge now on a postdoc position, but going to Texas A&M. His wife was going to be induced today. And of course, medical schedules, they schedule when they can schedule. So I thought that was, you get a lot of reasons why people have some issues of maybe agreeing several months in advance and not being able to come on. But I thought that was certainly a real valid one. So I'm going to try to substitute for him this evening. And then we have KT from Colorado, who is going to be our second of our presenters this evening. Welcome all for our May mini conference. I'm going to share my screen. Maybe I'm going to share my screen. Let's try that one again. Click on the right one. I'm going to talk this evening about is our concept of IPM appropriate for our pest in terms of our major pest, and that, of course, is the Varroa mite. All right, Kurt, is that up on full screen? Can you see the full screen now? Are we set?
Yep, you're good, Dewey.
All right, okay. So integrated pest management, is it viable for Varroa mites? If we don't get our questions, your questions asked, we recommend that you put them in the question function here. Kurt is going to monitor them, and then we can have questions from there, and or have you unmuted as we get along on at the end of our discussion. All right. Join you virtually this time again. As you know, for WASP, we're not scheduling a meeting this year, a live in-person meeting. We have a committee that working, and then we're thinking that we're going to have another WASP conference, and that will be in next year, 2025. This past Monday was World Bee Day. That came about by the Slovenian beekeepers as a petition to the United Nations. It took several years to get this designation of World Bee Day through. Of course, and that is one of the parts of the world where there's a very high honeybee density relative to number of inhabitants of the country. Many of them have their bees in buildings, and many of them use what we call the AZ hive. They call slightly different. And these are hives that open in buildings. The frames slide out, so you do all your inspection inside of a building. Just another neat hive system that is very common there in Slovenia. All right, there are a lot of definitions of IPM, integrated pest management. There's some other words for that as well. ICM, integrated crop management. So the concept basically is that crops, animals such as our bees have pests, and a strategy that of IPM indicates that we're utilizing multiple techniques to fit the context of each pest situation, with the long-term goal of reducing pest populations and pest damage. They indicated there are a lot of different definitions. This one comes mostly from entomologists in terms of our concept of what IPM maybe is. Okay. The big picture, we all know very definitely, certainly with our issues that we have with pests in our honeybee colonies, there are no silver bullets when it comes to managing them. Effective management involves many layers that can work together to reduce populations to sustainable thresholds. And sort of at the basics, this is what the concept is. You're using different types of efforts to try to keep a lid on, keep the number of potentially very harmful pests, whether it's a crop you're growing, whether it's an animal that you're keeping, et cetera, at a level that is manageable and is at a level where the system, the animal or the crop system, can tolerate that level without having an impact, an economic impact. Okay. The concept that we developed certainly for entomology, pests of insects of crops, for example, that we utilize thresholds to establish treatment guidelines. Once a threshold is met, an established threshold through research, looking at the pest, looking at the whole system, once that threshold is exceeded, then and usually only then treatments are used. They become necessary and then are used at that particular point. Treatments are selected and applied to minimum risk to human health, beneficial and non-target organisms, and the overall the general environment. Now, treatments can be of various natures, and we put labels on them. Treatments that don't involve chemicals, for example, treatments that we call cultural or mechanical, treatments that use another organism, biocontrol treatments. Okay. Sometimes we can group these together and saying like less invasive treatments. The concept of an IPM pest control is that these less invasive or non-invasive treatments are used first, and only if those options are ineffective, populations exceed a certain level, then our chemical treatments utilized. Our chemicals are then used. And in a balanced IPM system, there are multiple chemicals that might be brought to fore. We got to mute someone here. The chemical families, in effect, different chemicals with different modes of action. Their use is alternated, so it's not simply a chemical used time after time after time again. So again, there are many different possible definitions, but that's what I'm going to be working on in terms of trying to discuss. Does this work? Does this concept of IPM controlling our Varroa mite particularly work in our honeybee system, right? We know honeybees have a number of different stressors, from parasites such as Varroa, pathogens, poor nutrition, pesticides. We often label these as the 4 Ps. Sometimes I like to add yet another one, people, a 5th P as well. We're going to focus this evening on just the one pest, but this would apply to pathogens such as the foul brood pathogens, chalk brood pathogens, but it also can apply to aspects of the other stressors of bees. It can also apply to pesticides and poor nutrition. So it can apply to any. We're just going to use the Varroa mite, arguably our most serious pest with honeybee colonies as our model for this evening, for me to talk about this evening. All right. So the Varroa mite is a bit unique in that, but not necessarily the only situation where not only can it cause some damage by its behavior of its feeding on a host, in this case, the honeybee, but also in the sense that it is a vector. And in, of course, a case of honeybees, we know that it is somehow enhancing the duplication of virus within the body cells of both the developing pupae and from the adult as well. It's enhancing a couple different groups of the viruses. These viruses then can get to epidemic proportions. And so you can have a larger number of mites or a smaller number of mites, but then you've got the addition of the virus into the system because the mite, in doing its meeting its biological needs of a shelter and a food, et cetera, in the honeybee colony, is also vectoring or enhancing at least the duplication, replication of these various viruses that then actually can kill colonies outright, certainly adding a level of stress to the colonies and then may indirectly affect our fortunes with our colonies in terms of having colonies strong enough for pollination service or to produce our product of honey or whatever product we're harvesting from our colonies. So it's not necessarily the vector, it's the Varroa itself, but it's also its vectoring as well. All right. Some of those that we know that it may enhance are the paralysis viruses. There are not many symptoms that we can actually see, signs on bees, signals from our bees. Sometimes shiny or greasy, bees trembling, bees that cannot fly out front trying to get elevation and being unsuccessful flying, inside colony sort of stumbling along, having difficulty walking on the six-sided cells. There's an acute, and of course, there's chronic. There's an Israeli bee paralysis virus that has been implicated, at least initially to some degree, with the CCD. And then the second virus complex is the deformed wing viruses, depending how they are labeled. Sometimes A and B, sometimes as the deformed wing virus and the Varroa destructor virus, the VDW virus, etc. These will express, at least in some of the adults, with the shriveled or the unexpanded wings. But as in the larval stage, the pupa stage, we're not able to see an expression of either of these groups of viruses. These seem to be the two major groups of viruses that reach these epidemic proportions and then result in loss of colonies. And again, somehow by its feeding, the Varroa mites are enhancing replication of these viruses at the expense of all the other viruses that are in the bee system. And then these viruses will kind of take over, developing a life of their own, and then threatening or actually killing the colony itself as a stressor. So how do we put IPM really then into practice? And again, I'm just going to focus on Varroa mites. It starts with understanding life cycles. So we need to understand our honeybee, our host life cycle of queens laying an egg and individually in cells. Within 3 days, that egg then developing into the embryo, and then a larva as a result. Larva is the feeding stage, of course, 6 days, 5.5 days for queens, 6.5 days for drones. And then the cell is capped over. A prepupa spins a silken cocoon in that cell. And then the remainder of the brood development stages are underneath that capped cell, our capped cells or our pupa stage of development. And finally, after 20, on average, or normally under normal conditions, like 21 days, we get a worker that then ecloses, comes out from the cell, 24 days for a drone, and of course less for a queen. But we also manage the other cycle in our beekeeping, and that is the life cycle of the mite. The mite has a two-phase development. So as that cell is being capped, or just before, the female mite that is being hosted by an adult bee, whether it's a worker or a drone, is able to leave the host body and go into the cell. We call that then the reproductive phase of the mite life cycle, at which time she then will begin to develop eggs, develop and then lay eggs within the confines of the capped cell. And then depending on how long the cell is capped, be able to generally reproduce one more mature daughter successfully on average if it's a worker cell, and on average close to 3 new mature daughters if it's a drone cell in which what we call the foundress mite has entered that cell. There's then the second phase of the mite, and that is the dispersal phase. So when the adult bee that has been hosting the pupa stage that has been hosting a mite and her developing family when it emerges, then with the founder's female and one or more mature daughters, then are dispersed in the colony, and each of the mature daughters that has emerged with the host, with the newly emerged adult worker or drone, is able to then repeat that cycle, usually after feeding on fat body on its host, whether the host is a worker bee or is a drone adult bee, feeding and then repeating the cycle. So two phases really in the Varroa cycle. Why we need to understand cycles is, of course, we have this unique host, the honeybee, and the hot, dark, smelly confines of a bee colony, and what is the norm for its development, but also what is the norm in terms of the Varroa mite that it is hosting a population of in its same colony. So we need to understand the different phases, and by understanding these life cycles, then we're able to find external treatments, tools in which we can try to do something about the populations. Our beekeeping is management of enhancing populations, bolstering populations, feeding, moving frames around, etc. For that host, for our honeybee. So we're manipulating, managing in some way or other, and with our pest, we are basically seeking to enhance what the bee has as its own defenses against this pest. We're trying to find tools, mechanisms, managements, which we can use to also affect its population as well. So not only understanding the cycles, but understanding then their population cycles. So for most parts of the world, the bee development cycle looks like a bell-shaped curve. Numbers are very low in the dry or cold season. They grow in what we will term a spring, or when resources then become available, the population will increase. It will reach a population peak. So this is the blue line that is traced here. And then after that population peak, the numbers will decrease, first initially in brood, and then as the adults age, they die from the population and their population decreases as well. There are a few places where this is bipolar, but in many cases, this is sort of what the cycle looks like. And as we learn where we keep bees, we kind of learn what that cycle is of when they start in the spring, how we might manipulate or enhance that, how we keep them together as they reach a better condition, in other words, control swarming. And we can, to some degree, work with the timing of that peak. So the peak comes at a time when we have available and not in the environment where we're keeping the bees, the major nectar sources that are available for that colony, and thereby enhance our reward, our return in terms of honey. Now, the second population we manage are the mite population. Their numbers start low, simply as with a honeybee colony. They then grow. Their peak is reached at a period of time later in the season, after much of the honeybee population has already peaked and is on its decrease. They're at that point still increasing, and then they will then have a sharp drop in the fall, and in some cases that drop for our bee colonies too may be sharp. So it's both are depicted as a bell-shaped curve, but depending on some conditions, it might not be really bellish shape. It might be offset or skewed a bit. So that will vary certainly with locations where we keep bees. It's not the same in Florida as it is in the Central California and North Pacific Northwest and into Canada. Those curves are going to be slightly different, and that's one of the skills that we develop as we learn to have more experience in keeping our bees of this cycle, and when we can and should do things in our manipulations of either host, honeybee, or the pest, the Varroa mite, and when things are more effective in terms of what we might do in terms of our control. Now, and much of our information that we've supplied to our beekeepers we have looked at mite control at that intersection. As the bee colonies are size are decreasing in the fall, the mite numbers are still increasing. At that point, we're recommending sampling being done. And then this is when we have traditionally focused most of our control. What seems to be, and certainly should be in IPM more effective, is to actually work with the pest, is to work at the point where they start rearing they start ramping up that reproductive phase of their behavior and of their life cycle, and do our control at that particular period of time. Not after the numbers are very large. It has become very evident with the Varroa mite, because it is a vector of these diseases, the viruses, that if we try to control them on the back end after their numbers are larger, then we have the possibility that the damage that they've done in enhancing the replication of these virus diseases has already been done. And so in terms of a control strategy, if we seek to what became common when we had the pandemic with COVID, of flattening the growth curve, we would not have to have as drastic a measure that often was not totally very effective, because mite numbers were low, and particularly the virus had already had a chance to replicate and was then at that point a major stressor on our bee colonies. So early in a season, early in the growth phase. So in practical terms, that means now, that means in April, that means in May, having effective strategies for pest control, not in August, not in September, when it's very difficult to reduce mite numbers, but also the opportunity that the viruses have had a chance to grow and replicate in the body cells of the hosts has occurred for the majority of that particular season. Okay? So we need to understand both the pest and host populations, their life cycle, their basic biologies, and their population and their population numbers. Okay. Now, the concept that IPM basically works off of is that if we can do something, or our host has the capability of keeping a potential pest below an economic injury level, or an EIL, then that particular pest would still be in the system, but not at an economic level that it's going to affect, let's say, the harvest, or in our case, the potential for how much honey colonies will store, or how effective a colony will be as a population colony. So that by monitoring, by checking on that growing population through a season, there is an inflection point called an economic threshold, or ET, beyond which then that population of the pest is then causing some damage to the crop system, the host system of the animal that it is on. Now, it's going to cost us some money to affect some sort of a treatment, so that we additionally have a other level called an economic injury level, above which, that if we apply a control, avoid a pest population growing above that economic injury level, our cost of doing the control, our cost of affecting that control, then will pay off in additional harvest, or additional ability of an animal to be a more effective pollinator, or store more honey, for example. So there's both an economic threshold and an economic entry level. The red line here shows that we have our pest population. It starts at some low level. You just put a crop in the field, or it's those small number of mites that have survived over winter in our bee colonies. Their numbers grow. And at some point then, if it reaches this threshold, whether however we're going to define the threshold is just an economic. In other words, it's causing a degree of damage or an injury level, in which if we have apply controls, we can keep it below that level. Then that is our concept of pest management. We're not eliminating the pest. We're trying to keep it at a level that is not causing that level of damage. The dotted line would show that if we did not apply any controls at the point that it's reaching the economic threshold or prior to that as it's growing towards that point, so a pest population without control then would be a factor that is causing some damage to the host, damage to the cropping system. So if we can keep that pest population below an economic injury level, the cost of doing so gives us benefit in that crop or husbandry management system. Above the economic injury level, then the benefit is what we do can then affect the cost. If we do nothing, then we're going to be paying. We're going to be losing something. We're going to be losing yield. We're going to be losing efficiency of our animal system to grow, put on weight, or in our case of bees, of being able to store or be efficient pollinators. So that's sort of our concept of how we would look in terms of the pest. So we need to look at the various aspects that I've outlined in terms of what we think of as a system for bees, and particularly with Varroa mites, from this concept of IPM. So I mentioned initially that IPM one of its bases is that we have a way of sampling. We have a way of establishing a threshold. We have used in our honeybee system a system of where we sample adult bees. We wash them of their mites in one way or another. And then from that, we can then indicate a level that would be something that we can use as a threshold. How valid is that? So for example, in the dispersal phase of their reproduction, we can collect a sample of bees. Here we're collecting it into a white container. We then take half a cup, which is roughly 300 bees. And then we're going to wash the mites from those with alcohol, non-sudsing soap or whatever. And then we're going to count the number of mites. Now that number, then we treat that as a threshold number. In other words, to make the decision whether it's an economic injury level threshold or an economic threshold. Of course, we're going to, that's open to debate. So with our adult mite sampling of only the dispersal phase, we can then save hives. We recommend monitoring at least twice, more often initially, so that you get in the practice of doing so. And you all then have that continuing record because the population never stays the same. And then actions that are needed to take when the mite loads are over a certain number. We can monitor with sticky boards, sugar shake, carbon dioxide, alcohol, soap, wash, etc. Passive or active systems. There is equipment that is available to do all of those different monitoring systems. Now, it depends the time of the year when we do that monitoring, then what what we call our threshold might be. So if we're monitoring 300 adult bees, roughly that half a cup of adult bees, with hopefully an effective system of getting most of the mites that are on those 300 bees washed off the bodies and into the medium so that we can count it, so we can actually make a count. Spring development, when the mites are increasing their population, that would be for most of us in the Northern Hemisphere, March to May, what we call our population buildup. We're looking at if we have numbers over 1% infestation, then we might consider that colony at risk, and that would then trigger some sort of a control decision. For a summer sampling, June to August, near that peak population or around that peak population, the numbers increase to 2 to 3% infestation. In the fall, in August to October, when we would do the sampling, back to a 1 to 2% level of infestation. And of course, we compute that level of infestation by the number of mites that we wash off 300 bees times 100. In the winter, if we're affecting control, a period generally described as no brood, although in the southern states that's not true, then we can treat to clean a colony for spring. And so we don't have a quote a threshold because of the potential damage we're doing to the host by trying to take a number, so that without any attempt to come up with a threshold, we're going ahead and doing a treatment. So that is really kind of opposite what we're trying to indicate would be an IPM approach. Now, threshold considerations, I'd like to raise three aspects of that. And kind of our Bible is this the Honeybee Health Coalition's development of this tools for Varroa management. And so one of the questions we might ask is, where specifically does that 1 to 2 or 3% threshold suggestion come from? And those of you that have been following this for years realize that that number has changed. It's never been static. It has always been changing. So where does that 1 to 2% threshold suggestion come from? As principal author of Honeybee Coalition, I can tell you that number comes from my head. There's almost no data to indicate that 1, 2, 3, 10, 20, 40 is a threshold at all. That is kind of what we have adapted as what seems to be, if those numbers in spring jump up above 1% right away, that colony is going to be at risk of not getting through the season, not being effective in the season, or through the winter. So really, we call it a threshold, but it really doesn't have any very little valid research behind it trying to suggest that it is in fact a threshold. It is simply a number, something that we can look at. Second thought was, if we're going to do a sampling, 300 adult bees taken from some part of the colony, and there's been some studies that suggest that wherever you take them, it doesn't make a lot of difference, but we try to enhance that number by taking them from where the bees are likely to be hosting the dispersal phase, in other words, from the brood nest. But some recent work that's come out of University of Maryland, Zach Lamas, and when the USDA folks there at Beltsville, is demonstrating that actually the mites are not randomly distributed, okay? So if we're going to use a number that we have sort of picked out of the air, the basis of sort of doing that is that if any sample of 300 bees would be a representative of a randomly distributed organism, that might be a valid number in which to say, well, we have a threshold to work on. Well, as it turns out, they're not randomly distributed. And so, as any of you know, if you've done, for example, consecutive samples from the same brood area, 300 samples of bees, you don't get the same number. Often you'll get some numbers that are very wildly different. And yet the recommendation is, one sample and then determine a percentage, and on the basis of that, try to make a decision in terms of a level of risk that you might have. So the mites are not randomly distributed. So such a, in the middle of the year, when you might have a population of 40 to 60,000 adult bees in a colony, a sample of 300 in a non-randomly distributed pest is kind of really straining the thoughts of anything bordering on any type of accuracy at all. And then finally, the third consideration I'd talk about with thresholds is that we're monitoring only one of the two phases of our pest. We're only monitoring that dispersal phase. We're not do not have effective ways of monitoring for that reproductive phase of the pest of the life cycle of the Varroa pest. We're only monitoring one of two phases. Arguably, the reproductive phase is at least double, triple, perhaps as much as quadruple the amount of time that the mite is in the dispersal phase, and yet we don't have a way of coming up with any numbers to be able to sample that phase, the reproductive phase, or use that as suggesting that if we find X number, then that might be a decision in terms of a level of risk, or if you would, a threshold as well. So I think in summary, our concept that building an IPM program for Varroa mites, based on that we have something that we can call a threshold, is just kind of thrown out of the water, just not at all valid. So, is monitoring useful for Varroa control? Should we continue to preach that you need to first sample, monitor the number of mites in your colony, and on the basis of that, then go ahead and make a decision in terms of the level of risk? We know that monitoring of the adults is really not effective until that August period of time, at which time the mite numbers have really built up. Monitoring adults now, April or May in bee counties, is not at all effective. We get mostly zeros or under 1% levels, but it's not reflective at all of what the population, because at that point, mites are reproducing pretty much in a drone brood, not in worker brood. And so they come out on drone adults, and their dispersal phase mainly stay on the drones to be dispersed to go into additional cells to do another reproductive cycle. And so monitoring of the adults is not at all effective, particularly in the buildup phase of at least monitoring the dispersal phase of the mite itself, not their reproductive phase. So is monitoring useful for Varroa control? Is it useful for us to continue to suggest that people start in April or in May or in June and take a sample of 300 adult bees, and on the basis of that, make some sort of an informed decision about what's happening with the mite population within the bee colony? Now, our methods or our techniques that we can use, we base on our in IPM on our triangle, our pest control treatment triangle. And the basis of this treatment triangle is that we are hopefully working with that pest situation in the crop or the animal, initially in aspects of prevention and then intervention. And as we use different techniques in that triangle, we are working more on the aspects of trying to prevent the pest from growing to that economic level, injury level, or after it has reached that economic injury level, to do intervention. I've shown with our sampling that we have no idea where that level at all is with our Varroa pest in our honeybee colonies. And also in the triangle, we have an aspect that the toxicity of, in other words, when we are no longer using things such as prevention, but we are more going into the intervention, the level of toxicity of the products that we might be selecting is also increasing. And toxicity here is indicating their selectivity. In other words, selectivity for doing the damage to the pest, controlling the pest, and not doing all those other things that we're hoping is not also happening. The contamination in the environment, host potential issues to our own health, our water and our air that we breathe, etc. So let's look a little bit in terms of our IPM, in terms of our triangle. So fourth point I want to bring out in terms of IPM is that short of the chemicals, can other aspects of our IPM control triangle really work? So starting with our basis of prevention, less targeted, things that would help reduce the damage that the pest might do, the Varroa pest might do. We have things such as locating colonies, the size of the colonies, whether we do a lot of manipulations or few, giving colonies distinctive addresses so that we reduce the horizontal distribution of the mites. In other words, drifting drones going from one colony to another now, or workers later in the season. We've made concentrated efforts in this country in breeding to reduce the propolis envelope because it gets in our way. What is the level of propolis in terms of this cultural control? What kind of colonies we use, whether we're capturing colonies that have survived in the wild as feral colonies or unmanaged colonies, and using those as swarms rather than capturing other beekeeper swarms that come from the same stocks that we're having to deal with as well. When we have colonies that have too many mites that can serve as a focal point, since we take our colonies and we put them all in one location, whether it's 2 in a backyard or it's 72 in a drop from a commercial beekeeper in one part of one field, those that get too many mites, euthanizing those particular colonies. If we had a threshold, if thresholds were effective, we could do that. We could help reduce that effect. So those are some of the cultural controls. And so a good question is, do any of them work? Are any of these really very effective in terms of that distribution of mites horizontally from one colony to another, or vertically within the colony itself? Do any of these cultural controls really, are they worth the time and effort that we might put into them? Again, there's almost no research to indicate how much any of these might or might not be effective. We think some of them might be more effective than others. Distinctive addresses, certainly sunny locations. We do find that there are lower mite levels in bees in sunny locations versus shaded locations. And so our selection of an apiary site is not based necessarily on whether it's in the sun for the pest control or cultural control of the pest or not. And certainly almost no one euthanizes, okay? Climbing up our triangle, mechanical methods in terms of control are things such as using a trap, using a device. So things such as drone brood removal, brood breaks, or our screen bottom boards. Are any of these effective in terms of reducing that impact that the pest might have, keeping colonies below that economic injury level? We know, for example, in screen bottom boards that there is a small advantage, depending on a number of conditions, as a way of eliminating mites that fall from bees, but we've really not had much of a study in terms of those mites that fall from bees, are they at the end of their particular lifespan? How effective are those mites that fall off bees? As bees move around, how often do mites fall off from mites? We do know that they can reduce overall numbers, but it's usually pretty significant. And in my surveying here, I find that those that use the screen bottom boards have about a 3 to 4% advantage in terms of reduced mite numbers. But again, is it mite numbers that we should be looking at, or the fact that the viruses that are being vectored by the mites themselves? Now, the drone brood removal and brood bake are a couple other mechanical means of being able to do that. No real good rigor studies to show what they can do, but again, we do have some evidence that in fact both of those can be incorporated in our host management, our bee colony management, to try to combine accomplishing something with our colonies, and also at the same time having some impact in terms of the growing of the mite numbers, or what the final mite population might reach within a colony of mites. So both of those certainly as possibilities. I hope none of your frames look quite like this one. So this is a frame with some capped worker brood and lots of capped drone brood. And it's the work from the East Coast, Zach Lamas with his work in the Bee Lab at Beltsville, showing that because there is this non-random distribution of both phases of the mite life of their life cycle, both the reproductive phase and a dispersal phase. If we try to find where in this brood in the spring the mites might be located, we might find there might be some mites that are reproducing in a period that little part there of the drone brood, but that's a lot of drone brood. There might be a few more mites that are reproducing in that section of drone brood, and maybe a mite or two that's reproducing in that section of the cap brood. But if we sample any of the others, we're not likely to find mites. Mites are not randomly distributed in their reproductive phase. So how are we going to come up with a sampling technique to give a threshold of what, and then be able to accurately describe what in fact is happening? And then on the dispersal phase, as I indicated, it does not work to sample adult worker bees because these mites come out on the bodies of drones. Here we're looking at the underneath side of a drone with the foundress and 3 of her offspring, the mature offspring that she's able to affect by going into a drone brood versus a worker brood. And so during the spring of the year, the selection of the mites is in drones, both in the brood and on the adults. We have to date no effective numbers in terms of trying to sample either drone brood or sample drone adults in terms of trying to come up with a number, a threshold number, or a number that we can pin our hat on, that we can say that if the number is such and such, maybe this colony has a higher risk, or if it's below this number, perhaps the risk is not yet at a point where you might need to intervene in terms of any tools that you might bring to bear to try to do something about the pest population. Has it reached an economic injury level? We have no idea. We have no idea whether it's the reproductive phase or the dispersal phase, whether it's workers or adults of either drones or workers. Okay, and one of the issues that certainly we can point out here is that this mechanical device, that is drone brood removal, is a means of getting at the reproductive phase of the pest. That is that reproducing cycle that our pest, the Varroa mite, goes through. Formic acid, also one of our chemical tools, has that ability, but none of the other tools that we've developed really at all has anything at all to do with any aspect of control of the reproductive phase of the mites. Only these two really have much of a hope of getting at really affecting that particularly this time of year, April and May, that any change in the reproduction rate of mites and colonies. So our concept that we have developed is to work at this part of the year, August and September, trying to bring mite numbers down. But as I indicated, the level may already be at a point where the viruses have dispersed. We use the dormant period, or the broodless period of our colony, we're mostly broodless, as a control window. Without doing any sampling at all, just as a prophylactic treatment with either dribble or fumigation, sublimation with oxalic acid. And yet where we need that concentration is during this early stage of the reproduction phase of the mite, where it is growing its own population, the pest itself, so that come August, come September, instead of their population being that higher level, we then would have to deal with a much lower level of population of our pest, of the Varroa mite, a level that then we might also have more success with our other control chemicals. So that when we have our alert, control mites in the spring, on the right, a mite between the eyes of a worker bee versus on the left, by a mite on the eyes of the drone. If we uncap the cells, or if the workers uncap those cells, the bees are most likely going to cannibalize the developing pupae. The mite that's there, the founder's mite, will run out, and then she can start another reproductive cycle. But effectively, by uncapping us or the bees, we have reduced that reproduction of the mite in its period of time in the year when it's going to be able to begin to grow or drastically grow its own population. We do that, of course, with if we do that with drone brood removal, we have to manipulate our bees, manage our bees, so that we know where the bees in our colonies are raising drones. And then we have to harvest the drones at the period of time when the cells are capped, before the mites have had a successful reproductive cycle. If we don't do that, and don't do that in a timely fashion, we're just enhancing mite population growth by having a colony raise more drones than they might with our good, clean foundation, our good, clean, mostly worker cells frames. If we put that a drone frame in, or we're trying to grow drones, at least in this mechanical method of drone brood removal. Now, we've also brought into the formula another way of trying to keep mite levels down, and that is with a continuous use of oxalic acid, or what we call oxalic acid extended. And so that we would dissolve the oxalic crystals in a solvent, glycerin, canola oil, heat the material, dissolve it, and then soak pads of the material, and then have the oxalic acid in the colony for an extended period. The evidence seems to suggest that this is a method to keep levels that are low at a low level, to keep the colonies from being, the mites being very successful at growing their mite population. So it is a method a bit like drone brood removal, in the sense that it is, can be very effective in this period of time, up until we then can bring other tools to bear, trying to reduce the higher mite level, a higher pest level of our mites. The great advantage of all of this is then maybe that level is at a lower level, and we can then have more success in August, September with the controls that we do have available to get to reduce the dispersal phase, the phase of the mites on the adult bees, having our tools to be able to do it at that particular time of the year. So both can be very valuable techniques in terms of flattening that growth curve. One a mechanical, and other a chemical. But basically, we are applying these without knowing what is going on with our pest population. These are prophylactic treatments. We're on the assumption that the numbers are going to grow in the spring because of the life cycle of the mite, the fact that it needs brood to be able to reproduce, all of our knowledge of the biology, but we are basically seeking to use these without any aspect in terms of a threshold, or understanding what the level of risk might be in individual colonies. So then finally, our last aspect that we might look at, well, two more, I'm sorry, is biological. Sometimes we lump genetics in that with as well. We have no effective biological organism that's on the market, certainly at all yet, but certainly the genetic control has been one of our approaches. And we do know there are populations of bees that beekeepers generally do not need to do any or very limited efforts of trying to help the bees control the mites, because the bees are controlling the mites themselves. Populations from Cuba, from the south of France, the liver let die population from Sweden, population from Norway, example. We do have genetic bees, hygienic bees that are available, but they're of somewhat limited use because as we increase the level of hygienicity in our colonies, we bring our colony to risk of not having enough of a population to get through the wintering period, not able to raise a sufficiently large population of bees to live through the the season when resources are not available. So do we have alternative chemicals? Do the alternative chemicals solve our Varroa problems? So one of the last tenets to bring in terms of an IPM program is that our users, those that are ones that are suffering this issue from the pest, whether it's crop or animal system, have alternatives, have alternative means that would work. I've mentioned cultural, I've mentioned mechanical, not in honeybees, biological, that works in some other systems. But then our reliance on chemicals. And as I indicated initially, that in a definition of IPM, we're talking about IPM chemicals as being sort of the last resort, of being not the first line of defense in terms of combating that pest, but when populations of that pest reach or exceed that economic level, that threshold or entry level. Okay. We, in fact, do have alternatives. We call some groups synthetic chemicals, and of course, then hard chemicals. So for our treatment in the spring, now, this time of year, or later in the year when we're treating a higher mite population, we have chemicals of the thyme oil-based essential oils, Apigard, Apolife. We have a selection of 3 different acids: formic pro, formic acid based leaky hop guard, the acids from the processing of the hops, and the oxalic acid. Now, presently, we have only one synthetic, and part of our issue, unlike a lot of cropping systems, our users, our beekeepers have at any one time really have had only one synthetic. And the difference is that the so-called organic or the non-synthetic chemical compounds, such as the thyme oil, formic pro, the other acids, take very smart beekeepers to be able to use them effectively, because they all have some level of risk in terms of that they actually do what we want them to do, and the way that we use them or misuse them, and the way that we apply them. And of course, with both acids and the thyme oil products, there are issues with temperature. And we have the additional issue with our bee colonies that the bees themselves are controlling that temperature in their own colony. So as our last resort, do we really have that choice to be able to, on an economic basis, choose from those that might cost less or cost more, depending on what our level of risk might be? Crop systems can make that type of decision on their mode of action, on their chemical family. And we've really not had that in terms of our system. Yes, we do have the alternatives as shown here, but they're not all on an equal playing field. So it's very easy to use Apivar, a very effective material, before we've had this development of resistance, but the other materials are not nearly as easy to use and not nearly as effective, depending on some other factors: how we use them, when we use them, temperatures that we use them at, et cetera. So they're not all the same. I direct you to this particular publication that just come out from Vito Pharma, 22 of April. And what they are looking at is the relentless assault of Varroa destructor infestations of honeybee colonies is a global concern, propelling a race towards new pharmacological interventions. While conventional wisdom often emphasizes medication concentration as the linchpin of treatment success, the reality is far more nuanced. And so they talk about some of their own work that they have come up, Vito Pharma has come up with development of some of the chemicals. I direct you towards this fairly new, this past April, mid-April publication from Vito Pharma. Delaware Beekeepers just put out a bee health advisory based on the fact that in sampling of colonies in the state of Delaware, they've been able to demonstrate that there are colonies that seem to be developing resistance to the insecticide, the synthetic insecticide amitraz. Most of the rest of us, most of our associations could do the very same thing. We could put out a bee health advisory that that material is not working, or is not working to the degree that it was once at one time. And of course, from the USDA Baton Rouge lab, they're demonstrating that part of that is due to the fact that after many, many years of use, extensive use by at least the commercial beekeepers, it does seem that the bees are developing resistance. So this would be now in our line of synthetic chemicals, the fifth in a line that mites have developed resistance to our synthetic chemical. So our toolbox, what do we have in our toolbox? We have a bunch of different tools that we might use. When we go to do our own work with our toolbox, does your toolbox look like this? Is there one tool that can do all the various jobs that you might want to do around your ranch, around your home? Or should your toolbox look something like this? And so I use this analogy then, our toolbox that we might use for Varroa control. What does your toolbox look like in terms of what you're using for control of Varroa, assisting your bees? Since most of us don't have populations that can do it by themselves, of our management, our assisting of our bees. Are you relying on a tool, a single tool, attempting to use it and continue to use it extensively, or are you doing this IPM approach? In other words, trying to mix different levels of tools that we might use based on the IPM triangle, not relying strictly on determining a threshold, but making assumptions of what's going on in the bee life cycle. So treatment at a time when we're not sampling during the winter period, treatment at a time now when a colony is growing, the mite population along as the colony is growing. And again, not basing your assumption of a risk level on just the fact that you've made a determination of a level of mites that are in a colony, or for most of us with a apiary with more than one colony, of what the level might be in any one colony within that particular apiary. So you're treating not individual colonies, but whole apiaries, how many that number might be. So if it walks like a beaver, if it quacks like a beaver, now I must tell you that I am not at the University of Oregon. I am at Oregon State University. So that does not read ducks because we are the beavers. There's another university in Oregon that are the ducks. So if it walks like a beaver, if it quacks like a beaver, is it IPM? What does our crystal ball say? Very clouded. We're losing the most effective synthetic, apparently, to increasing levels of resistance. Alternatives are very difficult to use. We are having to base decisions on what we know about life cycles rather than on thresholds. We have no real effective threshold. So are we really IPM gurus? Are we very effective in terms of our Varroa mite control with an IPM approach?
Okay, great. Thank you, Dewey. We have a few questions that have come in.
Okay.
The first one, and this came in just for context. This first question came in when you were talking about the effectiveness of monitoring. And this anonymous attendee would like you to talk about monitoring Varroa to determine treatment effects, and the value of monitoring Varroa to determine treatment effects.
So our monitoring or sampling can be both aspects. We can do it as a level and thinking of a threshold in which we can base a decision based on some level of risk, or we can then sample or monitor following a treatment to determine, did what we think what we were going to accomplish by using that treatment, a brood break or use of a chemical, can we determine that the number of mites changed by our action? So indeed, those are those two levels. I concentrated on the first one of using monitoring as a level of determining a level of risk on which to base a decision to treat. But the second one, determining effectiveness of treatment, that is still an effective way to say, I think I was able to reduce the population by using this treatment. I can confirm it because the number of mites prior to treatment was X, and it's now at a lower level. It's X minus something following treatment. One of our issues with that is, what time do you do the monitoring post-treatment? Do you do it immediately with something like oxalic, where there is no residual at all of the treatment with fumigation, for example? There's no residual of the material. Powdered sugar dusting, for example. Yes, you can do that post monitoring right away. With something like the synthetic, with something where we're using oxalic acid extended, at what period do you come in and do a post-treatment monitoring? Because there can be some residual effect of doing the treatment itself. We don't have a lot of good information on when would be effective time to post-treat monitor.
Yeah, also from my perspective, and you mentioned this, there's the uncertainty of the monitoring itself that calls into question the value of post-treatment monitoring to determine
Exactly.
effectiveness.
Washing 300 adult bees, is that effective for treatment, for example, of oxalic acid extended?
Yeah.
We have no idea. We don't know at all.
Great. And the next question, and I see that there's some hands raised, and I'll get to those after the type questions. The next question, the individual wants to know if you can speak to the effect of genetic diversity on Varroa mites.
I cannot, and that's not my any area in terms of my expertise. We don't have an awful lot of information in terms of how diverse the Varroa mite population might be genetically. So no, I cannot talk to that at all.
Okay, and we have a few attendants, and we have a few panelists and one attendee who's permitted talking that have questions. So first, I'm going to go to Steve, the attendee. Can you unmute and ask your question? Okay, maybe they're not paying attention. We'll come back to them. Liz and Carrie, how about you? How about Liz? You go first with your question.
Dewey, I always enjoy your talks, and this was no different. Thank you so much for your presentation. I have a comment and a question. The comment is just that there's ongoing work from Mike Simone-Finstrom and Frank Rinkovich, who are collaboratively finding that there's an incredibly positive correlation between propolis envelope and Varroa counts being low. So that should have some numbers attached to it in the near future. And then with drone trapping, a conversation that I had as a grad student with Kirsten Trainer when she was at Beltsville. She was finding that drone trapping, if it's done correctly, where it's drone trapping rather than Varroa factory rearing, could reduce Varroa levels by as much as almost 85% within the colony. And that's the only number I'm aware of that's associated with that. But if you ever find a published number, I would really be interested in seeing it. And then my question was, in the time that I've been a beekeeper, which is 18 years now. We've gone from a threshold of 6 to this current threshold of 1 to 2%, which is, as you said, a very, very dynamic, changing thing. And so I wonder if you could speak a little bit about if you foresee that threshold continuing to change, because it seems to me like it's already about as far as it can go. Or if you would foresee instead a change in recommendations of monitoring and then providing thresholds for a different type of monitoring. What do you foresee being the future of this?
Thank you for your two comments on that's the first time I've heard a number 2 in terms of how effective drone brood might be. That's encouraging. That's quite a impressive number. I did make the comment on propolis that actually we've tried to breed out of our bees and our population, at least our American bees, our US bees, of that tendency to propolize. Maybe we've certainly got to try to reverse that in terms of breeding. Maybe that's going to be more effective. Now then to the question. So what does the crystal ball say? Where are we going to go? It doesn't seem like we're going to be able to reduce that number in terms of saying as we're using it as a number to peg a decision on, loosely saying a threshold. So I think what we need to do is refine the ways that we do our monitoring, and particularly if by trying to control the mites at the end of the season, many of us have remarked over the years that's already done its damage with the enhancement of those particular viruses. We need to keep the number low so that doesn't grow throughout a whole season. So we very definitely need to enhance our method of how we make informed decisions earlier in the season as that population itself is growing, mites are growing, how we make that assessment. And that means trying to determine what are the selection criteria of mites for the drones that they inhabit, in which they do their reproduction, and when they're on adults of the drones. So how do we enhance doing that sampling that period? I think that would be a good, useful step to try to flatten that mite curve, keep that curve down. So I think that's one of the ways certainly we will go. The effort to try to find a new synthetic miticide. So there is some federal funding on that. There's a consortium of US, Canadian, and European beekeepers that are looking at what some in the chemical company call those orphan chemicals. So there's a bit of effort in trying to find the next new synthetic that's so widely effective in terms of mites. The rate that the lab where you are, the USDA lab in Baton Rouge, has been demonstrating the advancing of the resistance to the amitraz. I'm not sure we're going to have that next level of synthetic or next possible synthetic available to our beekeepers to be able to use before we really have lost much of the ability of the amitraz to do the job.
Thank you so much.
Great question. Thank you, Liz. Carrie, go ahead. Okay, I'll give Carrie one more minute. Okay, we'll go back. There was a question that came in chat, Dewey, and Sandy would like to know if you could speak to organic chemicals and whether mites will develop a resistance to them. And if they do not develop a resistance, can you speak to the importance of rotating treatments?
So the IPM principle is that we do not use the same chemical or the same family, the same mode of action of chemicals, that we can rotate chemicals. And that's proven to be advantageous to cropping systems. Chemicals have had a longer lifespan when the people that need to control the pests have a variety of chemicals and that they can rotate. So that is certainly very valid in an IPM concept. The aspect of that then is we've never had the ability to do that rotation, simply because we are such a small industry, and there hasn't been an economic incentive for chemical companies to work on our system, our animal system of honeybees, to develop those chemicals so that there's more than one available at any one time. And that there's now, there's something in the pipeline to replace the one now that seems to be losing its ability. In other words, developing resistance by mites. Will the mites be able to develop resistance to these so-called organic or the non-synthetic chemicals? In other cropping systems where these type of chemicals have also been utilized, the short answer is yes. Pests are able to develop some resistance. We're still not able to answer a question of exactly how the acids are killing mites. We don't know the actual killing mechanism of what is actually occurring. So it's difficult to make a prediction in terms of how soon might that resistance develop to, for example, formic acid or oxalic acid, or to the thyme oil-based products, because we simply don't know what their physiological mechanism, how they're actually causing the damage to the mite, killing the mites. So we're a bit of a loss to say, yes, the mites are going to develop a resistance to these particular chemicals, or to this. We're using one essential oil, but we've been able to demonstrate that there are a whole bunch of others that also have some ability to work on mites and control mites. If we switch to one of these other essential oils, would the same mechanism be involved as with the thyme oil products, for example? We don't know. So it's again, it's a tough one to try to answer. But I would not count the mites out. I would not count out that just because we are using a very common acid, a very powerful acid, that the mites are not going to find a way to detoxify it in their own biological lifespan, life system, so that it becomes, the mite itself becomes resistant to, for example, a powerful acid such as formic.
Okay. And Carrie put in chat that there was an EPA issued an advisory January 2024 with 2 new Varroa treatments, including slow release oxalic acid strips. And she put the link there in the chat.
Yes, excellent. Excellent.
Okay.
And we're going to have a product on the market, Varroxan, which basically uses that very same technology. So it will quickly become a, quote, legal treatment, because we would then have a EPA registered product that in fact uses that same technology on the market. The second product, of course, is one of its issues for beekeepers per se, is that in most states it's going to be a group of registered under what we call registered pesticides, for which you need a license to be able to use them, whether it's your own bees or you're doing the business for other beekeepers of using that compound. So these 2 new products coming on the market are going to add to the tools, but they're basically variations of the existing tools that we have.
Great talk. Thank you, Dewey.
Thank you. I'll stop sharing. If your questions didn't get answered, here's my Oregon State email. I'd be glad to try to respond to them. Thank you for questions that we had. All righty. So with our mini conferences, we have the opportunity to, in one evening, to do two different types of presentations, sometimes very closely related and sometimes a bit different. Our second one this evening is from KT, what we call it is KT. KT is the coordinator for one of the newer state programs in terms of master beekeepers. This is in the state of Colorado. KT developed in her own training. She is a master beekeeper that went through the Colorado Master Beekeeper training, and as practicing chemist and teaching chemistry, she used some of that information to develop her own talk. So I'd like to introduce our second speaker, then Kathryn Thompson, KT. Welcome, and we're glad that are able to join us, and you're going to talk tonight. Well, you've already got your title slide up, so I'll let you introduce yourself and then also your title and what you're going to talk about.
Well, thank you, Dewey. Dr. Caron, like you said, I did go through the Colorado State Master Beekeeper Program and am now the director of the program. One of the things that I really like and am trying to really build into our program is, I guess, a sense of curiosity and what can we do to test the things you're curious about. And so, while I don't expect everybody to necessarily do a huge, publishable scientific research project, it is, I think, important for us to be able to foster that and expose our master candidates to that so that they can look at research and think about what it means and how it was prepared and interpret what it might mean to them. So I think that that's a really valuable component of our program as we get going with our new cohort of master candidates. So my project started, it's a follow-up from what I did for my master's research. And it started because I was a curious beekeeper and saw that I had bees that were foraging on the corn grain dust in the livestock feed on my family's farm. And so I investigated that. And my master beekeeper project was to look at the impact of that atypical forage, things they don't normally gather, and compare the development of young adult honeybees and then some colony level impacts, effects that were observed based on how they were fed. I don't have the right window selected, so it won't let me move on here. So I'll just introduce a little bit about honeybees and what made me interested in this, and then we'll get into my project, talk about how I did it, what I found, and what it may or may not mean. Honeybees, we know, are pretty widely imported, and especially here in North America, they are an imported species, not native. And so we find them foraging on things that they didn't necessarily, they didn't necessarily grow up with. They didn't evolve with, they didn't have access to in earlier years in their origin. So we find them doing things, especially as we keep them in domesticated situations, where they might have a dearth and not have access to forage. And maybe they're in a climate where it is warm enough and they think they should be out foraging. So they'll go out and forage. We do know when they bring home groceries, that nectar is their main source of carbohydrates. That is their energy to go forth and continue doing and being the busy critters that they are. But pollen is a really important nutritional source. It provides basically all of the other food groups for bees. They get their protein from pollen, they get their fats or lipids from pollen, and any other phytochemicals. There's some vitamins and minerals that exist in both nectar and pollen, but pollen is basically the rest of the food pyramid for our bees. We know that they'll go out and they'll bring nectar and water home in their honey crop. So they need that nectar for carbohydrates. They need to be able to find water. They need it metabolically just so that they can function the same way we need water. We don't function if we get dehydrated, neither do bees. And for swamp cooling in the summertime to cool their hive, they'll carry it in and deposit it and then let it evaporate and carry away energy. They also will go out and carry things back in their corbicular or their pollen baskets. There's one thing that they will carry back in their corbicular that's not a foodstuff, and that's resin, which becomes propolis in the colony. So I have a little picture of that up in the corner. But pollen comes in all sorts of different colors. Different seasons with different flowers will show you different colors. I should have taken a picture the other day. I was in a colony and they had black pollen, a navy blue pollen, and a bright scarlet red pollen, and it looked really dramatic. But a lot of times we see yellows and oranges and beiges and tans, and all those pollens come from different plants. And we do know that different plants produce pollens with different nutritional qualities. Some of them might be high in protein, some of them might be high in lipids, some of them, there's a particular phytochemical or lipid that you find in the pollen of borage, and it's in other plants as well, but in particularly high levels in borage, that is a essential fatty acid that bees need. So we also see bees gathering other things. So we know that the pollen is good stuff, and they'll gather a variety of it. But we also see them getting into other things. This first picture on the left is a picture of some bees in some chicken feed. And that might make sense. Chicken feed, especially if you've got laying hens, chicken feed might be 16% protein. That's somewhat analogous to what you might find in a pollen. The next picture, this is on my family farm here. This is an auger that handles soy pellets that we use to boost the protein content of our livestock feed for the livestock. And so it would make sense to see some bees buzzing around there. And you can just see, hopefully, you can just see the outlines of the bees. There's 3 of them there buzzing in towards the entrance of that auger to gather whatever dust is left up there. So that makes some amount of sense because the nutrition there is maybe somewhat analogous to what bees would normally forage for, even though we're getting into atypical forage, stuff that isn't normally part of their diet. The thing that I was noticing, because I do live on a relatively large farm, and we pretty commonly have a whole truckload of cracked corn ready to mix into the feed and feed to our cows and sheep, is that my bees would go out in force and gather dust off this pile of cracked corn. And you'll hear people with anecdotal stories about gathering the dust off of bird seed or, whatever they find. Maybe their horse's feed that might have some molasses in it. Well, that almost makes sense because molasses is sweet. Sure, the bees would check it out. But this is literally just a pile of dry, cracked corn. We do crack it on site, so there's a lot of dust in it. It's not had an opportunity to lose its dust because it comes out of the roller mill that produces it and into this stall here just as it is. And so there's plenty of dust for the bees to collect. And if my video works over Zoom, great. And if not, I'm sorry. Bare minimum, hopefully you can maybe hear the number of bees that are in this pile of cracked corn. It gets pretty dramatic. They actively pack it onto their orbicula. And there have been times during a false spring, especially in February here in Colorado, we get a couple weeks of nice weather when the bees are actively foraging and there's nothing out here for them to forage on. There might maybe silver maples or something would bloom, but we don't have those types of trees in my area. So it's really truly a fall spring. There's nothing for the bees to be gathering. So they end up in the corn grain dust. You can see there's quite a few of them. You can hear, hopefully. So for my master's degree, I investigated this. I put little groups of bees in hoarding cages and I fed them different diets. Some of them I fed 100% corn grain dust to. Some of them I fed a pollen substitute to. Basically, the idea was to try to compare the atypical forage the bees might gather to what a beekeeper might substitute those bees with if the beekeeper knows the bees might need it. So I did a kind of an assay where on one end they got 100% corn grain dust, on the other end they got 100% pollen substitute, and then I did levels in the middle there where it was a third corn grain dust, and then another level that was a third pollen substitute. I also, because I was new to keeping bees in hoarding cages in an incubator, wasn't entirely certain what amount of water to put in the syrup I was providing to them. They had free access to syrup, and it made sense to give them either 1-to-1 syrup or 2-to-1 syrup, just because that's what we would provide as beekeepers, but they don't have any access to other water. So I gave them one little pipette of water that they had free access to in the top of this cage, and in the other little pipette they had their syrup. Most of them I gave 1.5-to-1. So I kind of split the difference between 1-to-1 syrup and 2-to-1 syrup. And then one of them, I followed a standard research protocol that I had found and gave them 0.5-to-1. So pretty much, more diluted syrup than the other groups. And I'm glad I didn't commit to just one, because the only group that showed any signs of any disease or issues was that 0.5-to-1 ratio of syrup. They all experienced dysentery. I think maybe they just had too much water in their diet. So maybe they didn't need access to water and diluted syrup. But in my other groups that I fed the more concentrated syrup, I didn't see any signs of disease. And really the only thing that I learned was that if you take nurse bees shaken out of the colonies and put them in little groups of about 75 bees and feed them different diets of corn grain dust or pollen substitute, that they all die at about the same rate. I did not put my graph in here, but if you're interested, this is open access, so it won't ask you for money to pull it up. The only group that was different was in talking through this with all of my, local bee association buddies. There was an interest in, well, what about feeding supplements, things like Honeybee Healthy? And so I did do one set, a parallel experiment where some of the bees did get Honeybee Healthy in their syrup, and those bees did live a little bit longer, but it wasn't necessarily particularly significant. And I don't know why. Maybe when you take a bunch of queenless bees and put them in an incubator, the Honeybee Healthy, the essential oils in that Honeybee Healthy kind of mask the pheromone disruption of being queenless and not having any brood pheromone. And so maybe they just felt less stressed because they smelled more lemongrass oil. I'm not sure. But it is something to consider, I suppose. It's also possible that maybe that just stimulated more feeding and they ate more syrup than the other groups, and that for some reason led them to live a little bit longer. But this did stimulate me to think and be prepared for a master research project or master candidate research project where, well, didn't really learn too much when I did this in the incubator, but maybe there are some colony level effects that really, that's what we would care about as beekeepers anyway. The functional group when we think about the bee is the colony functioning, right? We don't necessarily care about 75 workers at a time. And so since I didn't find any real obvious effects, they don't die faster or slower when you feed them corn grain dust, I decided to do this on a colony level. And in setting this up, I did end up setting up colonies, but the data I gathered was based on the fact that we have evidence that the mass of the head might lead us to make some assumptions about the mass of the acini of the glands in the head. So the mandibular gland and the hypopharyngeal gland, which are important in feeding larvae. The mass of the abdomen without the digestive tract and the sting can lead us into some assumptions about the lipid body mass in the bees. Those are associated. And there's a correlation between lipid body mass and degradation of those hypopharyngeal glands in the head. So if the lipid body mass is decreasing, that indicates that the bee is also not healthy enough to maintain a large hypopharyngeal gland that would be able to produce lots of foodstuffs for larvae. And we also know that the hypopharyngeal gland content is correlated with larval nutrition. So in all these different ways that I can think about, well, if I look at a young nurse bee and I measure these things about her, what can that tell me about her ability to feed the next generation of brood and to maintain the colony population going forth? I also had a secondary objective because in talking to some researchers while I was setting my project up, I had one group of researchers who said, oh, you just do this, you dissect out the hypopharyngeal glands and you look at them under the microscope and you measure how big they are, and that tells you how productive those glands will be in producing royal jelly. And then I had another researcher who was very, very adamant that no, you really need to do a protein assay on those hypopharyngeal glands. You can have a huge hypopharyngeal gland that produces no good proteinaceous secretions. So I thought, well, if I can use my experiment as an opportunity to get some data and see if the size of the hypopharyngeal gland correlates to the protein content of the hypopharyngeal gland, I wanted to try that. And it so happens that bees have two hypopharyngeal glands, one on each side. So I selected one to look at under a microscope and measure the size of the little sacs or acini on the glands. And I set the other one from the other side of the bee's head off for protein assay. And I did the protein assays and I did my dissections, and then I had a computer issue and did not get my data uploaded before the computer crapped out, and I don't have the full set of data. So I haven't done anything with that purely because I lost the data before I got to analyze it. But it was a thing I tried for anyway. I did have several different treatment groups in this project. So I set up 36 colonies, and I had a negative control that had no feed, but were treated the same as all the others. So I set up new packages. I put a pollen excluder, and there's a picture on the next slide. I'll scoot over here. There's just this cheap plastic pollen excluder. It was the only one that I could afford 36 of at the time, and also manage installing 36 new packages and get them all installed and going. So I had 36 new packages. They all had a frame feeder full of syrup, and I maintained that frame feeder full of syrup throughout the experiment. They had free access to that. And the pollen excluder, sitting on the front, even in the control group, they had to crawl through the excluder. So I had a negative control that did not get fed and were excluded pollen. I had a positive control that I took the pollen from the pollen traps and made an actual fresh pollen patty with to feed that positive control, but they still had to crawl through the trap just to control for that variable that I had added a pollen trap. I chose a commercial pollen substitute to include, and for this one I used Ultra Bee. I chose that one purely because it's the only one that I found any controlled experiments on, and that in my brain I thought that would help my research have some place to sit in the body of works. And then corn grain dust was my fourth treatment group. So they all had a pollen excluder. And then I either fed them no patty feed, fresh pollen patty, Ultra Bee patties, or a patty made with corn grain dust. I did use recipes based on DeGrande Hoffman's research published in 2018. So those patties did have some sugar in them, and that made them, I guess, at least palatable to the bees. So they did eat them. And I didn't notice any differences in consumption rate or anything like that. All the colonies were from the same source, packaged and delivered on the same day. And I put them all in the same 10-frame equipment with one frame replaced with a frame feeder. And then when I was checking to see that the queens were laying, they were all laying. They all had about the same square inches of brood. And so I thought, oh, this is beautiful. They all look so similar right now. So I went ahead and started the experiment and closed the pollen traps. So they had to walk through the pollen traps, and then started administering the feed to the treatment groups. After they have been fed for I started the treatment groups on April 29th, and after they had been fed, I marked emerging bees. So I was looking for those really young nurse bees, and I wanted to get those really young nurse bees at the point at which their hypopharyngeal gland should be at their peak development, which is day 9 after emergence. So I started marking emerging bees. I guess it's 31 days after I started feeding the treatment groups. And then I went back to gather those 10-day-old nurse bees. So when I did this, I spent a lot of time watching nurse bees hatch or emerge, and I used different colors for each colony so that there was no chance of me getting them mixed up when I was doing the dissections. They were all cold anesthetized before I dissected anyone. But I made these little marks on all these freshly emerged nurse bees. I marked, I don't know, maybe between 70 and 90 in each colony every time I went, just to make sure that when I went back, I could for sure find 10 or 15 that were the right age. Just because I didn't know how dispersed they would get in the colony, or the other piece is when you're marking young nurse bees, their exoskeletons are still really soft and pliable. And I wasn't sure if I had accidentally damaged some of them. So I just erred on the side of caution and marked extras. So 10 days after they emerged, I went back and picked up the marked bees. The mass of the head and the abdomen, I weighed on a nice little sensitive analytical scale. And when you pull the sting apparatus of the bee and pull at just the right angle, the whole digestive tract comes out. Part of the reason why you would do that is to remove any meal that or anything that might have been in that bee's honey stomach. So we didn't want somebody who had maybe just eaten a whole bunch to have a much higher weight than someone who maybe hadn't eaten in a little bit, and have the contents of their digestive tract throw off the measurements. So I removed the digestive tract of each abdomen, weighed that separately from the head and I didn't actually weigh the thorax, but I separated the sections and weighed them. I did dissect out hypopharyngeal glands, but my data analysis, I should have updated this slide. It says it's pending. I did not get a full data set, so I think at this point it's probably not going to happen. But this picture here is from Corby Harris et al. They published a procedure for staining the hypopharyngeal glands. You can see in pictures A and B that these white hypopharyngeal glands kind of look like a string of pearls, I guess. And you can stain them blue so that you have a much better contrast, and you can measure the size of those little beads or acini on those glands to see how big they are. And then the second hypopharyngeal gland from the same bee went to a protein assay where we actually did a chemical test and used a dye that actually would bind to the protein and signal how much protein was in the sample, and used a spectrophotometer to actually measure the concentration of that. And that's more data that was on the computer that crapped out. I did, however, take multiple generations. The goal was to have several generations of brood so I could see if there was a trend over time with the different diets in the colony. And with the mass of the head and the mass of the abdomen, there is a trend towards decreasing mass over time. The first 4 columns in this graph have the mass of the head in the little, I don't know, kind of a dark tealy blue color at the bottom, and the mass of the abdomen in the orange color above that. And the first 4 columns are the first cohort of bees that I gathered. And the last 4 are the second cohort of bees that I gathered. You can see there's a trend where the second cohort of bees does have a lower mass of the abdomen. So that would lead to us assuming a lower lipid body mass, and therefore, because lipid body mass degradation leads to degradation of the hypopharyngeal glands, we would think that the hypopharyngeal glands weren't as healthy. But since the colonies overall had a big symptom, I did not proceed to gather a third cohort of bees. I wish that I had continued to gather samples, even though I did stop the experiment. But what happened was that they looked all really similar through the first 8 weeks. And by the end of week 9, the negative control and the corn grain dust treatment groups had less than 6 square inches of new brood. And so at that point, with less than 6 square inches of new brood, there wasn't really going to be a third cohort for me to gather from those 2 treatment groups. And it wasn't my goal to just kill all of these bees. So I decided to terminate the experiment and supplement feed and feed them back up at that point. It was like there had been a brood break. There were eggs the queen was continuing to lay, because I was in these colonies every few days for a little while. The queen was continuing to lay, but there was no young larvae. So I suspect that with no protein coming in, they were sacrificing the young larvae to maintain enough health to be able to support the queen and potentially recover when they did have nutrition. So I started feeding them back up. The brood nests expanded, refilled just fine, and I fed them all commercially available pollen substitute. They all got Ultra B at that point, and kept feeding syrup. I should have continued to gather bee cohorts, just because that would have been an interesting piece of data to see what would have happened after that, the feeding back up and return of the nutrition supply. But I guess hindsight is 2020, maybe. All colonies rated about the same going into the winter. So in late September, early October, I was thinking I did this experiment. They're looking good. I really thought they all had 8 to 10 frames. There weren't any patterns among treatment groups. So 8 to 10 frames of bees, I should say. And I didn't have to do any treatments for mites. My mite counts were never higher than 1.5%, so I did not use any chemicals. The 6 months, within 6 months of the experiment ending. But by the end of November, all of the negative control and corn grain dust colonies had died. So clearly there was something downstream that had happened. My particular situation, I think, might have had some confounding variables that might have impacted my experiment differently than, Emily Nordyke has done similar experiments where she, maybe not exactly the same, but she's done experiments where she used a pollen excluder and looked to see what the impacts of different things are on the bees in Florida. Well, in Florida, even with the pollen excluder on, there are enough things blooming that some of the pollen is getting in. Here in Colorado, during a drought year, there really wasn't a lot. And one of the things that I noticed was my bees were bringing in pollen, but that pollen was really dry. When I gathered it, it wasn't oily. It didn't stain my hands like usual. I've trapped pollen in my area before, and it usually is oily, and you'll get yellow or orange stains on your fingers when you handle it to clean it. And I didn't have any of that during this year. And I really think it was because we just had such a significant drought that the plants were stressed. So does that mean that maybe the pollen that my bees had access to as fresh pollen was maybe not as nutritious as it should have been? So that little bit that leaks through that plastic pollen excluder maybe wasn't good or wasn't good enough. Whereas in other places, maybe there would have been enough pollen that leaked through the pollen excluder to impact the experiment. I also think that we had clearly a population or a group, a cohort of nurse bees that were stressed and weren't wanting to raise bees and to raise brood, even though they had unlimited syrup. So clearly there was something going on that they didn't think they needed to raise brood. And when I gave them pollen substitute, they changed that behavior. So that nutrition did signal to them in some way that they could go ahead and raise a brood nest again. But did that lead to an overall decrease in their ability to feed the next generation? Like, were they so nutritionally stressed that they produced larvae that were nutritionally stressed because they weren't getting the same quality of royal jelly from those nurse bees that hadn't been fed properly, basically, during the experiment? I did note here, protein matters. What we see in studies with individual bees and in hoarding cages doesn't necessarily scale up to our colony level, which is the point of me doing the experiment. And I also would be really interested to go back in time and gather a sample of that pollen from the year I did this experiment and have it evaluated and compared to maybe a sample that I had in the freezer from a more typical year here. We have some research that's been published. I like Emily Nordyke's, I've misspelled her name on this slide, good golly. Emily Nordyke's experiment in 2021, where she used some blue dye to see who in the colony is consuming the pollen substitute that we feed to bees. I would like to do that with corn grain dust just to see who does eat it and where it ends up, and kind of compare that to Emily Nordyke's work. But overall, bees do a relatively good job of managing their own diets. There's work out of Juliana Rangel's lab where they give bees a choice between a high protein pollen and a high fat pollen, and the bees will select the one that balances their diet. So they do a really good job of doing that on their own. But when they don't have choices and they just end up scrounging around for whatever they can find, we end up with atypical foraging, like somebody's chicken feed or livestock feed, the corn grain dust. And that can eventually lead to nutritional stress, which leads to poor health. And I think one of the big pieces about our bee health is that it's this big picture. We have all these different variables that come together. And some of these variables we can't control, and some of them we can control. Maybe I can't control how many viruses my bees have, but if I can use a mite treatment to control how many mites are in my colony, that might help decrease the viruses, right? Just like we're thinking about after Dr. Caron's presentation. But I think nutrition is something that we can look at in our colonies to try to evaluate whether they have enough groceries coming in and whether we should consider supplementation. There have been some meta-analysis, and one of them is published by Emily Nordijk and Dr. Jamie Ellis, where they looked at all of this research on supplementing pollen, and they decided, well, maybe it doesn't actually matter. But I'm pretty convinced after my experiment that there might be situations where you might have a true dearth, and you shouldn't necessarily just trust that your bees will be able to figure it out. They can actually starve in some areas and some conditions. So, yes, here are my acknowledgements. Any final thoughts or questions?
Looks like we have one written down, and I have one too.
Excellent.
Why don't we do the anonymous attendee one first? Thanks, KT, for the great information. We do sometimes see bees visiting our chicken feeders as well. What are your thoughts on other types of atypical sources, such as crushed grapes from a grapevine in a vineyard and other fruit juices or concentrates? Are these healthy for bees forage upon?
Yes. Let me go back to my conclusions slide now that I'm seeing that. This one? So I think that if what they're getting is primarily analogous to what they would normally forage on, so if we think about crushed grapes, that's analogous to a nectar, right? There's going to be other stuff in a crushed grape, but it's sugar, right? And so they're getting carbohydrates. So I don't know that that's necessarily bad. I do think that there might be situations, there's stories of like bees in France feeding on the shells of M&Ms that have been discarded outside of the M&M factory and bringing back all these colorful dyes and making really colorful honey with it. I do think there's situations where maybe we might produce something, or maybe there might be a plant that produces something that could potentially be toxic to the bees, but there are even nectars that the bees just kind of generally don't bother with that could potentially be toxic. So I think they, for the most part, make good decisions when they have the opportunity to. They seem, I think especially after seeing Dr. Rangel's work, and the work that's come out of her lab, they seem to make good decisions to balance their diet if they have the opportunity to do so.
Yeah, I was in her lab when that work was done by Pierre and Alex. And yeah, I think you hit the nail on the head that when they have options, they can make good choices. But if they don't have options, then they really don't. There's also some interesting work from the UK from Jerry Wright's lab that was showing that some bees will prefer pesticide-laden nectar, so they can get their wires crossed sometimes too. It
Yeah.
looks like we've got one hand up on the panelists, and I also have a hand up. So why
Hi,
don't you go
JD.
for it, Dwayne?
Has your research caused you to change the way you feed your bees in any way? Do you have more food available? Do you?
Probably the one thing that I definitely do, and I don't know if this is necessarily advisable for everyone, but I do it all winter. I have one of those big blue pollen feeders. Actually, I have two of them because I have two apiaries. And I keep it full of pollen substitute, just dry pollen substitute all winter. because otherwise I know my bees are feeding on that starchy corn grain dust, and it's not analogous to nutrition that they need. They're just bringing in because they can. So I give them an option, and they prefer the protein in the pollen sub if I provide that as an option for them.
So do you think the bees have done better?
Yes, but then I also have to have swarm management skills because they have pollen all winter if they can haul it in.
Yeah, yeah. Okay, thanks.
Okay, this is Kurt. I think we lost Dewey, so I can try to moderate the questions. Thank you, Liz, for stepping in. I couldn't get to the unmute fast enough. And my a 5-year-old was talking at the time, so thank you. Liz, what's your question?
Yeah. So thanks for your presentation, Katie. I am wondering, just because pollen doesn't comprise as much of the adult diet as it does of the larval diet, if you got the opportunity, you think that it would be interesting to do your first experiment, but with in vitro reared or lab reared larvae rather than cage reared adults. And if you did that, what do you hypothesize the findings would be?
That would be interesting. I don't know that I've spent enough time thinking about this to know, but just in like it makes me think about the wanting to do Emily Dordyke's blue dye experiment at the colony level, because her findings were that most pollen substitutes weren't actually fed to the larva. They were consumed by the adult bees. And I think maybe it was Dedance AP23 was the only one that was actually fed directly to the larva. And I wonder if that's like, maybe it's the pollen substitute just isn't fed to the larva, but maybe because the bees have some protein coming in, they're not having to I don't know, sacrifice their own tissues to fuel their hypopharyngeal glands at the same level. So it would be very interesting to do a study like that.
Thank you.
Okay, we have one
Kurt,
question.
Kurt, this is Dewey. Yeah, we're dealing with a toddler here. I'm sorry, I wasn't right at the end there.
Oh,
I
it's
too
okay,
had a
Dewey.
question. I had a quick question for KT. You had indicated there were several different ways of looking at how nutrition might be measured by looking at adults. Did you as you looked at those various methods, did you think that that perhaps one was more valid or more valuable or more applicable than one of the others?
I think in looking through, there was a lot of research that focused on the hypopharyngeal glands, and I got hung up on the fact that there were two points of view about how to measure the hypopharyngeal glands, to the point that I didn't feel like I should trust that. And so it was more interesting to me to get the data set of all of the measurements and try to see the patterns among the data measurements. Like, maybe I took my experiment and removed it from my question a little bit, one step too far here.
Yeah, well, one of those measurements is just a morphological measurement, as I recall, right? Just measuring sizes,
Yeah. And really, at that point, I just thought, I'm dissecting these bees. I can throw them onto this analytical scale and see what the mass is. And I'm glad that I did, because if I hadn't done that, I wouldn't have any actual data other than my observations at the colony level, because I lost the data that I actually was aiming for it.
So in a master program, then there are inherent dangers or inherent issues, which many people might be thinking about. Well, I'm going to have some colonies, and I can do this experiment on colonies. Then there are those built-in inherent issues that might occur trying to do just a project that might be looking at something in colonies.
Yeah. And I think when you get to the colony level too, it's hard to have enough colonies and know that they're all similar enough that you can group them and compare them. So I think when we're thinking about, like a master beekeeping program doing master candidate research, I think colony level stuff might be kind of difficult if you don't have, I guess, too much of a farm to play with like I did.
Good observations. Thank you. Thank you, Katie.
And I still only had 36 colonies. So, there's plenty of, we'll say, pilot studies that have way more than 36 colonies. So
There's 2 more questions in the Q&A if you want to get to them, Dewey, or I can do them if you like.
Kurt, go ahead. You're doing a great job. Appreciate it. Thank you. Go ahead.
We have 2 more questions. So the first one is, in the natural condition, bees digest 40% of natural pollen. How does a commercial supplement, I'm a little, sorry, I thought I knew what this question.
Maybe it's compared to this.
Yeah. How do you compare
Correct
to your
us if we're
supplement?
wrong. Correct us if
Yeah.
we're reading your question wrong. So, different commercial supplements are going to rate differently, and I don't actually know the data on all of them. Like just some background information. One of the big expensive things in creating a pollen substitute for bees is milling the particles small enough so that the bees do digest it. And that was something that I was interested in when I was looking at the corn grain dust, and it is definitely fine enough that the bees can digest it, and they do have the enzymes to digest that starch. So they might be getting carbohydrates out of the corn grain dust. But I don't really know how much of each individual commercial pollen substitute gets digested. It probably varies by formula pretty significantly.
Great, thank you. And we have a final question here that I think they're asking for the mechanics of how you mixed the supplements with syrup.
So the commercial pollen substitute, I actually bought Ultra Bee patties that were already formed, and I just applied those to the colony. I usually cut them into thirds and applied similar amounts of patty feed to each treatment group. But I didn't actually mix anything for that one. For the others, I used a recipe. I think it's 2018. I have it somewhere in my PowerPoint here. It's at the bottom of one of these slides from DeGrande Hoffman's research published in 2008. Sorry. So what was the title of that paper? If we look here, we'll find it. DeGrande Hoffman, 2008, comparisons of pollen substitute diets for honeybees, consumption rates by colonies and effect on brood and adult populations. So I used a recipe published in that paper to make my fresh pollen and my corn grain dust patties. I did have to adjust the water content a little bit because the corn grain dust took quite a bit more water than the fresh pollen did.
Okay, great. We're at about time. Thank you, KT. Great presentation. Thank you for everyone for attending and participating. And thank you, Dewey, also for presenting. I hope you all have a good night, and you'll hear soon about our next mini conference. Thank you. Good night.
Good night, and thank you, Kurt, for filling in. And we will have a chance to bring Garrett back, Slater. He said that he would potentially then be available for our next one, which will be either the Tuesday or Wednesday, roughly the same week of June. So stay tuned. We'll get that information to you. Thank you. Good night, all.